The main objective of this lab was to observe the motion of an object that dropped from rest and fell somewhat slowly, and study the physics principles involved in this experiment, mainly Newton's second law. We then constructed a graph that compared the observed position versus time from our video analysis to the predicted position versus time of two different computational models, one that includes only the effect of gravity on an object, and another that includes both the effect of gravity and drag force on the object. After running the experiments, then we will study how the sets of data compare. Lastly, I will explore the hypothetical questions. We are interested in comparing the three data sets because we want to see which prediction model does a better job at predicting the observed motion, more specifically, seeing how adding the drag force affects the prediction model. For my lab, I chose an empty mango carton as my falling object in the system. The surroundings were me, the floor, and everything else in the room. Since the box was dropped from rest, we know that the initial velocity is zero. Using Tracker, I positioned the origin of the coordinate system axes to be located at the center of the carton. Aligning the y-axis such that the motion of the box as it fell was in the negative y direction. Using the program, I was able to collect the carton's observed position as a function of time. In order to construct the computational models to understand the observed motion of the carton, Newton's second law needs to be implemented into the starter code that we are given. Newton's second law states that the net force is equal to mass times delta V divided by change in the time. Since we are observing the motion of a falling object, velocity is changing, meaning that V final does not equal V initial, and thus delta V is a non-zero number. Net force is proportional to delta V. So if delta V is a non-zero number, then so is the net force. The net force being non-zero means that there's at least one force in the surroundings of the system that is acting on it. In this case, for my lab, I'll be looking at two forces that are acting on the carton: gravity and drag. The first computational model predicted the observed motion only including the effect of gravity, which is represented by the following equation. The negative 1 times j hat indicates that the carton is the model that includes the weight force and the drag force and the initial conditions from the video analysis are shown in the observed weight force plus the drag. We know that the initial velocity is starting to the air because we started the analysis analyzing the video. It causes the motion of the object to collect the data in this while loop in the code models the falling of the carton. A slower motion means that the object is coming from distance. The object was extremely model the weight force and I just had to choose my cause guess where it is therefore the net force acting having to estimate the velocity update formula or to run in the second and fast position update model of the center in t equals t plus delta. The model that includes both the weight model causing disparities predicts a way to limit sources error. This discrepancy could be attributed in constructing the second computational model and collecting the data and transfer mass. I added the drag force of the net force. The drag force is equal to negative v times the velocity. In many frames, however, the object was extremely blurry, the direction of the drag force, so I just took my best guess for where the direction of an object's motion. Having to estimate the center of mass could have caused me to over or underestimate the actual drag position of the center of drag of the object is proportional to the square of an object as it fell, likely causing the disparities on the graph. We can use this information to calculate B for the model. Possibly be to redo the experiment, but use a more opaque object so that I'll be able to identify the center of mass and squares it, computing B as the velocity changes after each change in time. Graphing the three data sets into one singular graph provided me with the following. The data can be observed by the blue dots representing the predicted data with the drag and gravity, the red dots representing the mango carton data, and the yellow dots representing the predicted data with no drag. All three data sets start at the origin because they all had the same initial conditions. They all move in the negative y direction, but at quite different rates. Neither computational model accurately predicts the motion of the observed falling object. The model that only includes the weight force increasingly overpredicts the observed falling distance of the mango carton as time increases. The model overpredicting the falling distance of the observed motion is likely due to the fact that it is not taking into account that the carton's motion is affected by an additional interaction with the surroundings, aka the drag force, in my analyzing the video. In order to collect the data in Tracker, I had to mark the center of mass of the mango carton by eyeing it in each frame. In many frames, however, the object was extremely blurry, and I just had to take my best guess for what the center of mass was. Having to estimate the center of mass could have caused me to over or underestimate the actual position of the center of mass of the object in different frames as it fell, likely causing the disparities on the graph. A way to remedy this source of error would possibly be to redo the experiment but use a more opaque object so that I will be able to identify the center of mass more easily. If the carton was initially thrown downward, the terminal velocity would be different from the terminal velocity in the case where the carton was initially dropped from rest. Throwing the carton down would mean that it would have an initial non-zero throwing force, which would in turn mean that the carton had an initial non-zero velocity along the y-axis. If we plug in an initial velocity in the computer model, we can see that the terminal velocities are different.